So thank you everyone to resist until the end. So now I'm going to give you an overview, an outlook on benchmark for graph stream processing. So for the sake of the presentation, I apologize in advance. I will give name to things which I know is controversial, but I need to explain what I mean with graph stream processing. So let's start with stream processing in a very simplest possible way. A stream of colored cubes, you want to sort it. So by processing one element at a time, you can imagine you are actually doing stream processing. You are in a stateless way, and you can do nice things like removing this element from the stream or splitting various colors. And if you want a real world example, I think this gives pretty much the idea of what I mean. One onion at a time, you can sort it out. The advanced version, which is more useful for analytical purposes, is the classical database approach, which is called data stream management system in the literature, and opens a window, like a temporal view over the data, and over this window is possible to perform a stateful computation. Continuing on the example of the colors, I can count how many colors there are in the stream. Now, what about graph? So in continuing on the example of colors, let's try to make it visible. So I take my naming from Vasia's survey, but adding something in mind. So let's start with streaming graph. Like as Vasia said, the streaming graph is a graph that keeps growing over time. Now I have a couple of edges. Everyone represents a color. Everyone represents a color. The number of vertices is not bounded. I can discover new vertices over time, and the circle around the vertices represent time. So the more time passes, the more edges I discover, the more nodes I discover, and potentially growing infinitely. Okay, this is a streaming graph. The challenges here are maintaining the graph over time, computing queries on a continuously evolving. Sometimes the graph evolves while you are executing the graph algorithm. So how does that impact the execution? I can also put some bounds on the graph. Okay, so if you imagine the graph as a circumference, you might have a perimeter, a diameter. So we know when where the graph ends, but it can be dynamic. So it means that over this graph I have changes. I can have addition, like in this case I add one edge to the two nodes, the burgundy one and the green one, or I can have deletions. In the sense I want to eliminate this edge here, and the graph the edge will disappear. Sometimes the addition and deletion are expressed in terms of fixed set of vertices. Sometimes the vertex can also be infinite, but still the overall size of the graph is bounded in memory, and I can compute, and this adds some characteristics to the computation. Now, the case of graph streams is, to my view, which come from like a hybrid world of stream processing, a subcase of this. Every element in my stream of color now is a graph itself, and my window over the graph represents the scope of my dynamic graph. Intuitively, what's inside the window is a dynamic graph that I have to maintain. I can imagine every element entering the window as an addition, decomposing the graph that represents the single individual element as a set of edges to add. And similarly, I can do the same thing with the graph that is going out of the window. OC stands for opening and closing point of the window. Now, this creates new challenges because in the window, I can have contradicting information because I cannot control. For example, I can have a statement that says the status of a door. Door is open, and at the same time, the door is also closed because both the edges are concurrently present inside the window. Sizing the window is a very important problem, which is not trivial to solve. I've been working on a sub-case of this case of graph streams, specifically for RDF, which to the comprehension doesn't add much. The graph internally is an RDF graph. Actually, we have some perks in the example. Typically, Sparkle queries extended to stream as well. They run under the unique name assumption. So some subcases of this contradiction, they solve themselves. some other don't. So what we end up doing is retaining the latest possible occurrence of a certain assertion. So if an edge happens to be timestamped with a newer timestamp, I keep that one as a source of truth. Now, the state of the art of RDF stream processing is quite niche. It's an intersection of different communities. Most of it is semantic web, sufficient big participation from the stream processing community, being 2 depth challenges in RDF stream. There is some work on logical reasoning applied as well. And of course, streaming weekend data publication. But I'm going to focus on the green side, which can be seen chronologically like this. Everything started in 2008 with the streaming knowledge base. Then there were a bunch of systems were developed over time, system and query languages that extend Sparkle for continuous processing. With continuous processing, I mean that out of a stream of data, I will receive a stream of answers. Immediately the community realized that they needed the benchmark to actually have a fair comparison. So we had from 2012 to 2015, we have a series of benchmarks. The latest one is stream WhatDiv, but the most popular one is CityBench actually. And then a new wave of systems, Stride that implements the same ideas on top of Spark streaming. And then the latest one is RSP4j, which I am an author of, and is actually trying to give a library for fast prototyping.
3 minutes.
So let's give you a panoramic of the usual suspects. So this benchmark that sign a point of change. LSBench is the first one. Social media domain, so it's very simple, synthetic workload, and combine static and streaming data. Unfortunately, it's not portable. The code doesn't really run everywhere. Although it's scalable, there is a generator and measure max throughput and memory consumption. Then we have RSBench, which instead is a set of data sets from the weather hurricanes from US. Unfortunately, the data only are given non-generator. Queries are also available. And the only KPI was query coverage. So they was checking if the various query languages could express the required information needs. CSBench extends vaguely SRBench by making the query parametric. So it adds some sort of scalability measure, and it also introduces a notion of correctness of the results. CityBench, which I said is the most popular one, is actually on a smart city scenario. Real world data from Arus, static and streaming joins. Scalable because there is a query generator. The portability is in the sense that most of the time, whoever used the benchmark, they implement the annotation. I know it's on in the papers, but then a lot of KPIs, throughput, latency, memory consumption. So a lot to talk about. Finally, stream WhatDiv, in my personal taste, is the best. User activities over web, click streams, static and streaming data, test drivers, so it's easy to run. Queries to use, generator for query and data, throughput and latency as a main characteristics. Is the most recent, so it suffers from that, but it will keep up. And finally, I will just want to mention the Debs Grand Challenge 2017, which is also user activity, real data in RDF, and measure throughput. Unfortunately, it doesn't scale because the data are kept from the Orbit project, so they're not available unless you ask for it. Now, why am I showing you this? Because the goal of a domain-specific benchmark is foster technological progress by guaranteeing a fair assessment. That's Jim Gray's word, not mine, which means that like in the past, things were done in a certain way, at a certain point, a person arrives and change the word, and then we can see how the men's high jump world record, which by the way this year is an Italian who won it, change and scale out. So we have the same opportunity. We can introduce through the LDBC, by working together, potential for technological progress. We can push the state of the art further by introducing workloads and data generator that improve this domain for a more generic and comprehensive graph domain, not just RDF. But we have some lesson learned that we can build on, and I think that's nice. In conclusion, I want to say that RSP4j, this library for fast prototyping, can run as a test driver. So it can provide a code base that we can start with. We won the best paper award at ESWC. So please check out the repository, use it, and that's it. If you have questions.
Thanks, Riccardo. So are there questions from the outside the room, let's say from Zoom? We still have energy for questions.
We're all hungry.
Short of time. Okay, so it appears not to be the case. So is there so are you so what would be your, so you're basically proposing or asking whether there should be, whether LDBC should go into this graph stream processing?
I think there is an opportunity there, yes.
So my question is, I mean, in a way, the way that the SNB data generator for interactive works is you do get a stream of well, updates at least, and you also get in a way a stream of queries. So isn't that already close to what you're looking for?
So, yeah, I see an overlap. What is missing is continuous queries, in my opinion, in that benchmark specifically. So we need to think some queries that represents meaningful work to executing streaming, a query that whose answer changes over time. That's the missing point. And also the financial benchmark that they were presented sounds like an interesting addition. Mm-hmm. So I see the ingredients are there. We have lesson learned, potential starting point.
Okay. So you would say that potentially in the financial benchmark, you could envision standing queries, like, okay, those queries that would immediately detect a cycle.
Yeah, an example.
Once a change is made, that could be
absolutely
of interest.
One example is detecting fraud identities. That's a standing query that because the person that is trying to cheat keeps changing his information.
I'm not sure what the end group thinks about that, but maybe I definitely invite you to start a discussion with on that topic.
Great.
With that, though, we are out of time, and I would like to thank Riccardo